Hello class. Today in Lab 7, we'll be learning about topographic maps and groundwater. Topographic maps show Earth's three-dimensional landscape on a flat 2D surface. They use contour lines, which are lines of equal elevation, to represent the three dimension and help us visualize hills, valleys, and slopes. Most USGS topographic maps are quadrangles, which are rectangular areas defined by lines of latitude and longitude. These standardized sections make it easier to compare and connect different regions. To locate features on Earth, we use a grid system based on latitude and longitude. Latitude lines run horizontally and measure how far north or south you are from the equator, which is at 0 degrees. The poles are at 90 degrees north and 90 degrees south. Longitude lines run vertically and measure how far east or west you are from the prime meridian at 0 degrees, extending up to 180 degrees in both directions. Together, latitude and longitude coordinates let us pinpoint exact locations on a map. Topographic maps use scale to shrink real-world distances. A common scale is 1 to 24,000, meaning 1 inch on the map represents 24,000 inches in reality. Bar scales and fractional scales help us measure distances accurately. This scale is also referred to as the map's ratio. Contour lines are the heart of topographic maps. Each line connects points of equal elevation. The contour interval tells us the vertical spacing between lines. Here, it's 20 feet. Index contours are the bold lines, usually every fifth line, that helps us to quickly read elevation. There are 5 key rules for contour lines that we'll go over next. First, contour lines never cross, because a single point on Earth can't have 2 different elevations. Second, contour lines always form closed loops. Even if the loop runs off the edge of the map, it still closes somewhere. This rule helps us identify features like hills and depressions. Third, when contour lines cross a stream or valley, they form a V shape that points upstream. This is called the rule of V's, and it helps us determine flow direction. Fourth, the highest elevation on a hill is just below the next contour line that would appear. Finally, the fifth rule states that the lowest elevation in a depression is just above the next contour line that would appear. These rules help us estimate elevation extremes. Contour lines describe the landscape based on their spacing. When contour lines are close together, the slope is steep. This is typical of cliffs or mountainous terrain. When contour lines are far apart, the slope is gentle. This is common in plains or rolling hills. Topographic maps let us calculate relief, which is the total change in elevation, and gradient, which is the slope. Gradient is calculated as rise over run, which is the elevation change divided by the horizontal distance. Here is an example of gradient. A trail drops from 1,060 feet to 960 feet over 4 miles. That's a 100-foot drop over 4 miles, giving us a gradient of 25 feet per mile. This tells us how steep the trail is. So now that we've talked about topographic maps, let's move on to streams and groundwater. Where water ends up is important to us because water is a vital resource. As we already know, ocean water makes up the largest percentage of all water on Earth, and only a small fraction of Earth's total water is freshwater. Within that small fraction, most freshwater is locked up in glaciers and ice caps. The rest is groundwater, and the smallest portion is surface water. Streams are natural systems that move water and sediment from higher to lower elevations, shaping the land as they flow. The path a stream takes is controlled by topography. Large streams are called rivers, while smaller ones are known as creeks, brooks, or rills. There are 2 main types of streams: perennial streams, which flow continuously and are connected to groundwater systems, and intermittent streams, which only flow at certain times of the year. Streams play a key role in transporting materials and connecting surface water with groundwater. Most towns and cities are built along streams because they provide essential resources, fresh water, food, transportation, and recreation. Streams also supply water and nutrients for agriculture. Beyond human needs, they support ecosystems and continuously reshape the landscape through erosion and stream migration. Stream systems are made up of three main components. Tributary streams collect water and sediment from across a drainage basin. Trunk streams carry that collected water and sediment downstream. Distributary streams release water and sediment at the stream's base level, the lowest point the stream flows to. Overall, streams follow the path of least resistance, shaping the landscape as they go. A drainage basin, or watershed, is the land area that collects and directs water into a specific stream. For example, the Mississippi River Basin drains water from much of the central United States. The boundaries of a drainage basin are marked by high points, like ridges or mountains, that separate one basin from another. Streams can form different channel shapes depending on slope, sediment, and flow speed. Straight channels are rare and usually occur in steep terrain. Braided streams have multiple interwoven channels separated by sediment bars, common in areas with high sediment load. Meandering streams curve back and forth across gentle slopes, creating wide bends in floodplains. Stream shapes and patterns are influenced by geology. Regional geology, like rock type, slope, fractures, and faults, affect the overall stream system pattern. Local geology, such as gradient, sediment load, vegetation, and climate, determines the shape of overall channels. Together, these factors create distinctive patterns like meandering, braided, or dendritic streams. Stream discharge is the volume of water flowing past a specific point in a stream over a set period of time, measured in units of volume per time. Measuring discharge helps determine water availability and reveals how human activity affects water sources. A recurrence interval measures how often random events, like floods, have occurred in the past to estimate their future likelihood. A key tool in geology and hydrology for assessing risk. For example, a 100-year flood has about a 1% chance of happening in any given year. Streams and groundwater are closely connected parts of the water system. As surface water moves through a landscape, some of it seeps downward and becomes groundwater. Groundwater isn't an underground lake or river. It fills the pore space between grains of rock or sediment. It's stored in the saturated zone where all pores are filled with water. Above that lies the unsaturated or vadose zone, where pores contain both air and water. Let's define these zones more clearly. The vadose zone, or zone of aeration, is where water can still drain downward under the pull of gravity. The saturated zone lies below it, where water is held in place by pressure and fills all available pore space. The boundary between them is the water table, which rises or falls depending on precipitation, pumping, and other environmental factors. Groundwater is replenished or recharged by precipitation, surface water, and irrigation. It can also move sideways through the subsurface from one area to another. Eventually, groundwater discharges into streams, lakes, or the ocean, or is removed by wells. The rate and direction of this flow depend on two key properties: porosity and permeability. Porosity describes how much open space a material has to store water, and grain size can influence this, though storing and grain shape often matter even more. Permeability describes how easily water can flow through those spaces, which depends on how well the pores are connected. Together, these properties determine how quickly groundwater travels and how much water an aquifer can hold. Permeability describes how easily water can move through connected pore spaces. A material can have high porosity but still be poorly permeable if those pores aren't well connected. Permeability controls how fast groundwater can flow, which we can measure using hydraulic conductivity. Materials like sand and gravel are both porous and permeable, making them ideal for aquifers. This slide helps visualize the difference between porosity and permeability. A low material can have high porosity but low permeability, like clay, because its pores aren't well connected. In contrast, clean sand has both high porosity and high permeability, allowing water to move through it easily. Understanding this distinction is essential for predicting how groundwater will flow. Aquifers are geologic units that can both store and transmit water, so they require high porosity and high permeability. Sandstone and limestone are common examples of good aquifers. Confining beds, such as clay or shale, are much less permeable and act as barriers to flow. These layers can trap water above or below them, creating confined or unconfined aquifer systems. Unconfined aquifers are open to the surface and are recharged directly by precipitation and surface water. Confined aquifers, on the other hand, are trapped between impermeable layers that place them under pressure. When a well taps into a confined aquifer, that pressure can cause water to rise on its own, sometimes all the way to the surface, creating an artesian well. When groundwater is pumped faster than it can be naturally replenished, aquifer depletion occurs. This lowers the water table and can lead to serious consequences, including land subsidence, which is where the ground surface actually sinks. In coastal regions, overpumping can also draw seawater inland, causing saltwater intrusion that contaminates freshwater supplies. When a well pumps water, it creates a cone-shaped dip in the water table around it, known as a cone of depression. If many wells are pumping in the same area, these cones can overlap, lowering the water table even further. This can reduce the yield of nearby wells and impact surrounding ecosystems that depend on shallow groundwater. Subsidence occurs when groundwater is withdrawn and the weight of overlaying materials compress the now dry sediments. As the pore space collapses, the ground surface can sink, forming sinkholes or causing permanent loss of aquifer storage. Once those pores are compacted, they don't reopen, even if the aquifer later refills. Groundwater and surface water are tightly connected. When groundwater is overdrawn, it can reduce the flow of water feeding wetlands, rivers, and estuaries. This disrupts ecosystems, increases salinity, and can degrade water quality. The Everglades are a classic example of how reduced groundwater levels can alter an entire landscape. Groundwater is vulnerable to pollution from both natural and human sources, and once it becomes contaminated, it's extremely difficult and expensive to clean. The Cuyahoga River fire in 1969 became a national wake-up call about water pollution and helped spark major environmental reforms, including stronger protections for both surface water and groundwater protection. Pollution can come from point sources, like a leaking storage tank, or from non-point sources, such as widespread agricultural runoff. Non-point sources are harder to control because they diffuse and come from many places at once. Stormwater runoff is a major contributor, carrying nutrients, metal, and other pollutants into groundwater. Stormwater runoff is especially problematic in urban areas. As it moves across pavement and other hard surfaces, It picks up everything from oil to fertilizers and carries these pollutants into nearby waterways. In the 1960s, Lake Erie was famously declared dead due to severe nutrient overload, which fueled massive algal blooms, a process known as eutrophication. Common sources of groundwater contamination include fertilizers, septic systems, landfills, and hazardous waste sites. The ChemDime Superfund site in Ohio is a stark example. Hundreds of thousands of gallons of hazardous waste were stored in barrels that were simply set on the ground. Over time, the barrels rusted and leaked their contents into the water system. Cases like this highlight how vulnerable groundwater is and how difficult it is to restore once polluted. Protecting groundwater requires careful management, responsible land use, and ongoing monitoring. For the lab, I'll post another tutorial that walks you through the Excel portion. If you have questions, review the lecture videos and slides before reaching out. Good luck!